With each enamoring picture caught by the James Webb Space Telescope, it keeps on getting thought from different corners of the universe, including planets within our own planetary system. A year earlier, we considered our most memorable brief look at pictures showing the Carina Cloud, the Stephan Quintet, and strikingly, the spellbinding Deep Field picture. This specific image evidently portrays various universes loosening up into the gigantic spread of the universe, fulfilling the presumption made. The James Webb Space Telescope hasn't stopped to amaze. It has, as of late, revealed objects that challenge established cosmological ideas. These dumbfounding discoveries are now marked as universe breakers by cosmologists, bewildering the scientific community with their capacity to challenge existing concepts. The reasons for these discoveries remain shrouded in mystery, tossing our hypotheses and speculations into confusion. So, what's the latest scoop from the James Webb Telescope? What extraordinary new discoveries has it revealed that were previously unknown to us? Join us as we dive into the discoveries of how the James Webb Telescope has introduced proof suggesting the presence of another universe, testing the norm understanding of the Big Bang. Our universe, as we've long perceived, emerged from a hotter, denser state via a hypothesis known as the Hot Big Bang. This idea, a huge scientific accomplishment throughout the last century, gained overwhelming support during the 1960s with the discovery of the cosmic microwave background, CMB, a remnant from the early hot and dense state. Over time, the Big Bang has remained the prevailing theory explaining our universe's origins. However, new and critical observations have driven cosmologists and astrophysicists to question both the ongoing expansion and the Big Bang itself. Despite these difficulties, alternative hypotheses have failed to gain momentum, stressing the enduring nature of the theory of the universe's origin. According to the general perspective, the description of the universe's beginning involves a smaller, denser universe in the distant past. The presence of radiation like photons shows that the universe was hotter at its beginning and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels reach a point where a singularity could form, and the ordinary laws of physics break down, around 10 to the power of 43 seconds during the Planck time. In such a brief period, small distances, brief spans, and high-energy scales challenge our understanding. Rewinding the cosmic clock to the speculative zero point, if the universe began as hot and dense, it would have expanded and cooled, producing a vast number of particles and antiparticles, with excess particles annihilated by radiation. As temperatures decreased, the breakdown of the electroweak and Higgs balances led to the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The combination of protons and neutrons led to the formation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions underwent growth due to radiation pressure followed by gravitational collapse, leading to the formation of large-scale structures. Around 380,000 years after the Big Bang, the universe cooled enough for stable neutral atoms to form, marking a critical step where photons decoupled and their frequencies stretched as the universe expanded. The discovery of the cosmic microwave background decades ago solidified the theory of the early cosmic explosion as the most supported explanation for the universe's creation. #the debate, Big Bang versus steady-state theory. While most cosmologists and astrophysicists embrace the Big Bang theory, staunch defenders of the steady-state theory, like Fred Hoyle, continued to support increasingly unlikely ideas, only to face defeat in light of overwhelming evidence. The proof presented was decisive. It wasn't fading starlight or reflected heat from dust. The cosmic shine showed an astounding consistency in all directions, resembling an ideal black body, but it had no connection to known objects in the universe. Despite this, Hoyle and his followers continued to obstruct scientific progress by supporting empirically misguided ideas. Meanwhile, the fields of space science and cosmology underwent tremendous development from the 1960s through the 2000s, with cosmology experiencing especially striking progressions. We outlined the vast universe and described its structure on a grand scale. We investigated the development, evolution, and dynamic interactions of galaxies and their stellar populations. Nevertheless, in spite of these advances, we encountered anomalies that challenged explanations within the framework of the Big Bang theory. Observations uncovered inconsistencies that challenged the predictive power of the theory, most notably the absence of exotic relics predicted by the theory, such as magnetic monopoles or particles from grand unification. The universe we observe today appears to require forces beyond our current understanding, yet these remain elusive. At its inception, the universe required a precise expansion rate to balance the total energy density, an achievement that the Big Bang theory struggles to justify. This led to neither firm equilibrium nor sufficient time for energy exchange across various regions of space, given the universe's vastness and its expansion over time. These anomalies present significant challenges for cosmology and the scientific community as a whole. ###, the inflationary model and its challenges. When existing theories fail to account for observed anomalies, two approaches arise: refine existing hypotheses or consider alternative explanations. The theory of inflation emerged as the most promising structure for extending the Big Bang perspective. Inflation proposes a period of rapid expansion, smoothing out the universe and imparting uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. Inflation's predictions align with observed patterns and fluctuations, supporting its validity. While alternative theories exist, inflation's scientific strength remains unmatched. However, despite past contributions to general relativity and singularities, Roger Penrose's work, along with his collaboration with Stephen Hawking, failed to match the progress of inflation in explaining the universe's earliest moments. Recently, there has been deliberate work to undermine the credibility of inflation theory, pushing for formal cyclic cosmology instead. However, this theory is intrinsically flawed from a scientific perspective. The key difference lies in their predictions. Conformal cyclic cosmology suggests that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of the universe. Conversely, inflation theory maintains that the end of inflation and the hot Big Bang are causally disconnected from any pre-Big Bang region. Each aspect of our universe shows remarkable characteristics suggesting that we should rely on the universe itself to reveal what is true, rather than simply relying on theory. ### James Webb Telescope's surprising discoveries. Space experts quickly recognized anomalies in the images sent by the James Webb Space Telescope since 2022. These discoveries may require a reassessment of key aspects of the universe's origins and evolution. One major discovery made by the Webb telescope was the presence of fully formed galaxies much earlier than expected by the standard model of cosmology. This anomaly challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by galaxies. Such revelations disrupt our understanding, akin to encountering grandparents described as children in a story. Additionally, recent evidence has uncovered inconsistencies within the fundamental theories of the universe, such as the ongoing error in determining the Hubble constant, which persists despite improvements in data precision and collection methods. Further, new data from the Webb telescope intensifies existing challenges to the current cosmological model. These issues highlight flaws within the model, prompting questions among space experts and physicists. While the model has undergone changes over the past 50 years to align with emerging data, some argue that these adjustments have been overly accommodating. As a result, there is growing recognition that a shift in perspective might be necessary, potentially reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe in the 1920s. Subsequent revelations, like the cosmic microwave background radiation in 1964, confirmed the theory of the universe's origins, depicting the early universe as a hot, dense soup of subatomic particles gradually cooling over time. ### rethinking cosmology in the light of new evidence. Achieving the current level of accuracy in cosmological understanding has required theoretical extrapolation beyond observational data. The concept of endless expansion, proposed in 1981, was introduced to resolve inconsistencies in earlier Big Bang models, further emphasizing the dynamic nature of cosmological theory. According to this model, the early universe underwent rapid, extraordinary growth for a brief period following the Big Bang. While certain issues are resolved by this idea, new challenges arise, especially in light of the prevailing belief in the existence of a single universe. Perhaps there are countless others beyond our observational reach. Certain detectable anomalies, such as hypersingularities within black holes, find support through indirect evidence. However, the astounding discoveries of the Webb Space Telescope regarding the arrangement of galaxies and the ongoing issue with the Hubble constant raise concerns that we might be approaching a tipping point where a significant overhaul of our current cosmological model becomes necessary. This could require a reassessment of the fundamental building blocks of the universe, including the very nature of existence itself. Cosmology, unlike many other scientific fields, deals with fundamental questions about the universe, its origins, and the role of observers within it. The study of consciousness and quantum physics explores similar topics, investigating the intersection of theory and reality. Testing core assumptions, such as the stability of physical laws over time, has been proposed by researchers like Roberto Mangabeira-Unger and physicist Lee Smolin, who suggest that physical laws may evolve and change over time, challenging the standard worldview. Physicist John Wheeler even proposes that each observation can influence the universe's past and future, radically reconsidering scientific practices. It is essential to examine these foundational assumptions, given the impact of theoretical presuppositions on data collection. History has shown that disruptions in scientific thought, such as the shift from geocentrism to heliocentrism or the revelations of evolution and relativity, have led to profound changes in societal perspectives. A similar effect on our understanding may be forthcoming from any impending scientific revolution in cosmology. Philosopher Robert Cotton argues that theory becomes crucial when further scientific inquiry fails to provide satisfactory answers to a question. The ongoing debates within scientific communities about whether theory is required to address cosmological fundamentals suggest that, if modifying existing models proves inadequate, a complete overhaul of our understanding of the universe may become necessary. #the role of the James Webb Space Telescope. Recent advances in observational technology have revolutionized our understanding of the universe. The James Webb Space Telescope, with its cutting-edge instruments, allows cosmologists to peer further back in time than ever before, capturing light from the early universe that has traveled billions of years to reach us. This ability has transformed our view of cosmic history, uncovering patterns and anomalies that challenge long-held beliefs. One of the most significant implications of Webb's discoveries is the potential for rethinking the timeline of cosmic development. For example, the discovery of mature galaxies only a few hundred million years after the Big Bang raises questions about the speed and nature of galaxy formation. This observation suggests that the processes governing star and galaxy development may have been more complex and efficient than previously understood. The ramifications of these findings challenge assumptions about the ongoing development of cosmic structures and propose that large-scale star formation may have occurred much earlier than current models predict. Furthermore, the detection of unusual patterns in the cosmic microwave background radiation, combined with data from Webb, suggests that our universe may be more homogeneous and isotropic than the Big Bang model can fully explain. This has sparked discussions about the plausibility of a multiverse, where our universe is just one of many, each with its own unique properties. Such a worldview would not only reconsider how we understand physical laws, but also expand the limits of scientific inquiry. While we may not be able to directly observe other universes, as astronomers continue to analyze data from Webb, the potential for discovering exoplanets in habitable zones around distant stars has reignited interest in astrobiology. The study of conditions on these exoplanets could yield insights into the chemical signatures of life beyond Earth. Researchers are especially eager to identify biomarkers, substances that could indicate the presence of biological processes. This search could ultimately lead to profound philosophical questions about our place in the universe and whether we are alone in the vastness of space. Furthermore, recent discoveries from Webb have prompted a reevaluation of dark matter and dark energy, two of the universe's most puzzling components. The inconsistencies observed in galaxy rotation curves and the distribution of large-scale structures may suggest new particles or forces that differ from existing theoretical models. The James Webb Space Telescope continues to unravel the mysteries of the cosmos. Its discoveries may prompt a profound paradigm shift in how we understand the universe. The telescope's ability to peer further back in time allows scientists to gather data from earlier stages of cosmic evolution, possibly providing a glimpse into realms of the universe that were previously unreachable. The detection of galaxies and structures that formed much earlier than predicted by current models suggests that the processes of galaxy formation and star development could be far more complex and efficient than previously thought. This raises the possibility that the universe may have undergone different phases of evolution, or even experienced previously unknown mechanisms that helped shape its growth. Furthermore, the Webb telescope's extraordinary sensitivity could lead to breakthroughs in understanding the role of dark matter and dark energy, two of the most enigmatic and unexplained aspects of our universe. While the existence of dark matter has been inferred from its gravitational effects on galaxies, and dark energy is thought to drive the accelerated expansion of the universe, neither has been directly detected. Webb's data may provide clues as to the nature of these unseen forces, offering a clearer picture of their influence on the universe's structure and behavior. The telescope's observations might also shed light on the long-standing question of whether dark matter and dark energy are part of a larger, unified framework or represent entirely separate phenomena. Moreover, Webb's exploration of exoplanets, particularly those in the so-called habitable zone, where conditions might be conducive to life, is ushering in a new era for astrobiology. This search for potentially habitable worlds around distant stars holds the tantalizing promise of discovering life beyond Earth. The identification of atmospheric compositions, chemical signatures, or biomarkers that could indicate biological activity would not only redefine our understanding of life's potential, but also ignite broader questions about the nature of life in the universe. Could life exist in forms radically different from what we know? What conditions are truly necessary for life to flourish? These questions could radically transform our understanding of biology, evolution, and our place in the cosmos. As more data pours in from the James Webb Space Telescope, it becomes increasingly clear that we may be on the cusp of a new chapter in cosmic exploration. One that may force us to reconsider not just the origins of the universe, but also its broader implications for life, existence, and the very nature of reality itself.